multiple modules from mathematics, like ordinary differential equations, some of programming stuff. So in my session today, I'll be covering portions. Today, I'll be covering portions from linear algebra, and I'll show some of the programming stuff which are very, very basics, assuming that many of you are very senior faculty members in your college. And also, some of you might be beginner to Python, so it will be very easy, some programming stuff that you can just quickly reproduce and you can do similar program in your computer. And part of the course today, I'll be covering some basics, and tomorrow bit advanced things related to quantum computing, applications of linear algebra. Although the language of quantum computing is linear algebra. So as much as we can learn this subject, so it is good for us to understand quantum algorithms in detail, right? Well, so with this, let's start, and let me know whether my this whiteboard, today it's blackboard, okay, and my voice is clear, my board is presentable. Can anyone confirm so that I can start? Thank you so much. So you are open to ask any question on the chat box. I'll be looking at, and it's although it's difficult sometimes to get things done on online, but let us try at least so that we can make this as comfortable as possible. Okay. So those I think many of you already have the very good background in matrix algebra, right? Those who are pretty new, and might be some of you are from outside circuit branch or computer science branch. I mean, electrical engineering, EC, or mathematics. Some of you might be coming from finance. Some of you might be coming from biotechnology, material science. So these are some of the books which may be good for you to get introduced to the formally to mathematically to the subject. Okay. And so those who are very new, they should start from these three. Okay. Introduction to Linear Algebra by Professor Gilbert Strang, and he just a retired professor from MIT. And if you have time, and if you want to understand the geometry of linear algebra, I should always prefer to visit this lecture series on linear algebra, right? Um, so it's nice to get a good exposure on linear algebra by Professor Gilbert Strang. And in YouTube, you can just simply search on linear algebra by Gilbert Strang. There are about 35 lectures. So um, at least you should visit 20 lectures, 25 lectures, or if you can complete it, this is good for any subject in engineering in general, right? Not only for quantum computing. Now, to understand in a bit more, at least various norms, various matrix properties, and certain things like condition number, stability of engineering system, etc., etc. This book is pretty good. Matrix Analysis by Hahn and Johnson, right? And especially for quantum computing, I will suggest, because most of the problem we solve, right, in quantum computing, you will see they are basically eigenvalue problems, right? Like uh, I'll come this part, eigenvalue problem. So in quantum mechanics and quantum computing, you'll see you are given an observable, right? Say, okay, you are given a Hermitian matrix H, right? And you need to find the ground state of a given quantum mechanical phenomena for this provided Hamiltonian H, right? So often you solve Hx equals to lambda x equation, right? So this kind of thing. Sometimes you are given an operator, right, corresponding to a observable lambda, right? So basically, any physical operator you'll see, because they are real quantities in physics. For example, energy, momentum, right? position, right? So so all these are basically eigenvalues, lambdas. They are real eigenvalues, right? Corresponding to an operator. And that operator has to be Hermitian operator. So that means O star equals to O, right? So O is a mathematical operator here. So like A transpose equals to A is a symmetric matrix, right? And if A star, that is a complex Hermitian part, the transpose and complex conjugate. So A star equals to A. So this kind of consideration, then we find the eigenvalues of this kind of matrices as real matrices, and several quantum algorithms will be learning just based on this particular equation, right? So it is good to understand what is lambda first of all, then what are the properties of lambda. If this matrix A is a non-Hermitian system, then what is the consequence of lambda, right? If you have underlining some nonlinear system, right? So can I bring some notion of polynomial of eigenvalue or not? Say for example, a square if I do, right? So is a square. So basically it's like this. So you have an input x, it's passing through a square system, right? A into a a multiplied system a and a, right? And you get output y. So what will happen to the output just by multiplying if the system is like this kind of polynomial system, right? So it has a direct consequence in the lambda, right? So we'll read those things. So basically function of a is also a function of lambda, and there are certain theorems. So these are the important things. And just to get this kind of flavor of lambda various properties with respect to matrices, and of course you won't get the quantum flavor in this book, but at least the mathematical background is very good to understand the quantum mechanical phenomena later on from this book, Matrix Computation by Golub and uh, Loan, right? So these three are the main textbooks for this next today, tomorrow, and next week. I'll also take some classes on probability theory and its implications on quantum measurement and error mitigation stuff. Although I won't do more on the algorithm, but I'll do on the mathematical background part, which will be required in your QT-05 on quantum computing algorithms, right? Okay. So now let's start and let's go slowly and let me know if you are stuck anywhere. If you find difficulty in identifying my handwriting or anything or any queries, I often do mistakes, so please stop me anytime. I'll rectify myself also. So yeah. So let's start from something that is this basis, right? Because okay, rank and all the stuff, I assume I'll share a note. Please just have a go through if you have forgotten those concepts. But something that is important relating to our quantum computing stuff, so I'll start from that point, and that is the orthonormal basis set. Okay. Right. I have a number of lectures on linear algebra as well. You may have a look in this MNIT QT series on AICT courses. So I'm going a bit deviated from there every time. So I'll start today from this point, orthogonal basis set. Okay, so an orthonormal basis set for a vector space V is a set of vectors. So two things are there. One is orthogonal, and why I am covering these portions, I'll come. Okay, so one part is the orthogonal part. So that means every pair of distinct vectors are orthogonal. That means suppose I take two vectors, say x and y, right? These are two vectors, right? and they has to be they have to be orthogonal, means their inner product x and y bar equals to 0. And second thing is normalized. Okay, so that means each vector, this x bar and y vector and y bar, they have this norm equals to 1. Okay, these two properties are important. Then I'll say that um, that the so I can form a vector space V, right? And which will take basically x bar, y bar, and this to satisfy the vector space property, you can take 0, 1, and all those just for the things. I'm keeping it just empty, right? So then basically we call this set of x and y, right, as the orthonormal basis set. Orthonormal basis set, and it is extremely important, right? So now let's take some example, and then we'll see why it is so important, not only in quantum computing but also in chemistry and other thing. I'll give some examples. So first is for a set of vectors. Now just instead of x and y, let's take u1, u2, these all are vectors, to un, right? and and so I'll say that this set of vectors in an inner product state space is orthonormal if, just I'm rewriting this part, that if ui comma uj, these two vectors dot product equals to lambda ij, I can write. Okay, so so basically if I equals to j, then only I get 1, and if I not equals to j, I get 0. So just same definition I'm writing in terms of the delta function, right? So now you can ask me why these things is so important. So any vector typically, say from our childhood, I mean when we studied in school, and we learned that any vector r, and it is represented say 2 I cap plus 3 j cap, this kind of representation. Now what is this I and j? They are unit vectors, right? This I and j are unit vectors. So that means this I cap and the j cap, their dot product equals to 0, first of all, right? And I say that towards this x-axis direction and towards this y-axis direction, the norm of this x, when it is equals to 1, say this unit, right? And just I am putting a direction, and I am calling this vector as I with unit norm equals to 1. Similarly, towards this direction, j vector, right? So any vector I can represent using this orthonormal basis sets, right? Now I say, so of course, these two I cap and 3 j cap, that this particular thing, right? So this is 2 unit and this is 3 unit, right? So 2 I cap and 3 j cap. And in the vector notation in computational science way, we write this as r as a variable, right? 2 and 3, right? And also sometimes we call this a row vector. Row vector. So in general, if nothing is stored, then we often represent in this way, 2 comma 2 3 in this downward positions way, and actually it is a column vector, right? So basically it's like a column, right? So row and column are more, it's easy to define from the matrix. Basically, I'll come later, but for now, so this is just a representation of a vector in 2 and 3. These are not just element. but they can only be represented using certain computational certain basis sets like I and j unit. This is the in the Cartesian coordinate system. These are just I and j, right? Something like that. Now on the quantum side, we learned about qubits, right? First of all, this is a vector quantity, okay? And that's why I started the session with this vector algebra. So vector quantity, right? So if my information is a vector quantity and not a scalar quantity, like in the classical bit, so like 0 and 1 string, right? So this is often we write as a this way, binary, right? So any binary string number, so typically we write in this way, 0 and 1, and if it is n bit string, we write n in the upper thing. So so this is basically, if you look at information itself are individual discrete component and they are typically scalar quantities, right? Or just coefficients, right? And they do not need the notion of this dimensionality in terms of representing in the vector space, but in the quantum information, we need a vector representation of the information, right? First of all. So I was representing, so we were representing the quantum state ket psi, right? At say alpha times 0, what it is. Oops. Alpha times 0 plus beta times 1, right? So, and I'm not going to the introduction of this part from quantum physics or anything. Now, what does this mean from linear algebra? That is important, right? So this 0 and this 1, so let's again draw this this kind of Cartesian coordinate system, and this 0 and 1, suppose this is my 0 and this is my 1, and this 0 and 1 are basically my orthonormal basis. Orthonormal basis. Next week, I'll define this 0 and 1 in a very different way from probability theory. But today, this 0 and 1, they are simply vectors. And this 0 is basically a vector of 1, 0, this column vector 1, 0, and this is basically 0, 1, right? So if it is 1, 0, and if it is 0, 1, and you can simply do the dot product between 0 and 1, and you can see it is equals to 0. The dot product between these two vectors, right? 0 and 1, right? Just simply dot product, it will come as 0. So that means they form an orthonormal basis set. Now I can represent my quantum information. Suppose this is my quantum state ket psi, right? And then there are two components, right? So one component is the alpha components towards this 0, alpha times ket 0, and one is the beta component towards the basis ket 1, right? And then the natural question is how to get this alpha and beta. So my state was ket psi, right? Now, if I do a mathematical projection, I'll come to detail, a bit detail of what is projection, what projection means. But now it's a simple, simply just uh, if I do a projections of this quantum state, just a projection on this state, right, psi. So you'll get the shadow of this thing on the this particular 0 axis, right, or x axis, right? If this is your x axis or ket 0 axis, and if this is your y axis or ket 1 axis, and if you simply project this quantum state on this particular x axis or ket 0 axis, right, what you get, you do 0. So better to write this way. Ket 0 alpha 0 plus beta 1, right? And this 0 times 1 will be equals to 0, but 0 times 0, this unit, this basically unit vector, right? And from the just the definition of orthonormal basis set here, you can simply write it as alpha times 0, 0 plus beta times this 0, 1, right? So this part is 0, right? And this part equals to 1. So you get alpha, right? And if you take the square of this, you get alpha square. So this is equivalent to quantum postulate number 2, right? So basically psi square x, if psi x is your wave function, psi xt is your wave function, so square of this gives the probability, right? So so basically it gives the probability. And I'll come directly from here next week on the probability theory. So this is exactly, you do the projection of the wave function in a particular quantum basis states, right? This is what actually we call this 0 and 1 as computational basis states. Computational basis states. Nothing is written here. Something is hidden, you call vector, state vector, computational basis state vector. This is often hidden, we don't say this word, but this is there. So these two are vectors, right? And why I say computational, because 0 and 1 are computational bits, so that's why we call computational basis. And state vector, okay, they are vectors, and typically they are orthonormal vectors, and you represent your quantum information just any vector. If you want to represent on a plane or on an n-dimensional space, you need n-dimensional n basis states, orthonormal basis states, right? So similarly here, I need to represent two level quantum information, so I need two orthonormal basis states, 0 and 1, right? So now what happens? So similarly, if you do dot product between 1 and psi, and if you do the square, you will be get beta square. So this is just to get the probability notion, but just simply if you do 1 and psi, that means you project the quantum state on the vector, orthonormal vector kit 1, you get beta, and that is the projected part. And that is basically beta part of your quantum information. And this is exactly what is called the quantum measurement. Okay. Quantum measurement in projection wise. Okay, there are other quantum measurement like POVM and other things. So I'll come later on those parts. But simply this is one of the quantum measurement methods. Okay. So so this is something important, and this is so important because this is not just because of algorithm, but this is used in many cases. For example, sometimes you got some signal, speech signal, for example, right? Um, so you have some say composite speech signal, right? And there might be some frequency component which are important, and you need to identify. So this is a two channel, some particular signal, right? So or it can be your just 2x2 MIMO communication system, and you want to identify certain parameters from this communication channel matrix. So whatever it is. So suppose this is some signal, right? And just by giving in the time domain representation, it is difficult to understand t versus y to find out what is the frequency distribution, right? So that's why we take the help of the tools like Fourier transform and Fourier series, right? So what typically we do, this information, when you discretize this, suppose clear version is something like this. This is suppose the superimposed version, right? And we do discretizations, right? So basically, then discretized part, this suppose this is y0 to yn minus 1, right? So y0 to yn minus 1, and you denote it as a vector, say y, right? This is your vector. And suppose you want to represent this particular vector, and it is now in the time axis, right? And you want to represent into some other axis, right? Some other representation. So that means just you are trying to represent these things in some other basis sets other than this just this xyz thing. So this is Cartesian xyz, but suppose basically this particular thing is basically time versus the amplitude, t versus amplitude, right? But we may need to represent the same particular vector in other basis sets. So that's why you can represent your information y, which is a function of t, y is a function of t, if it is that is the case. Then this is sum of some Cn e to the power Jn omega naught t, right? And this is say n equals to minus infinity to infinity, if that is the case. So this is just a linear combination of the trigonometric basis sets, right? And this is exactly what is called Fourier series representations, right? Similarly, for the other basis way, right? How you represent your same vector or information in the wavelet basis. So there you need to find those bases and those particular coefficients to represent your information, whether you can extract it better way, right? So in chemistry, people are basically always try to find certain basis set, and they have particular representation of the wave function. Say for a benzene molecule or a nitrogen molecule, right? They need to represent the fermionic representation of the molecule, right? Uh, o- so so they need to represent xi, say this particular wave function as m equals to 1 to n c mu I and phi mu r. So this kind of representation. So this is the basis set and these are the coefficients, right? And how you can represent your wave function in a particular basis set in whatever way. So there are the particular representation sometimes called the Hartree-Fock state. Sometimes it is like STO, some 3G or other like NG, right? Slatter type orbital, planar wave basis representation. So these are various way how you represent your information in the basis set, particular how you efficiently can represent your information by expanding into the basis sets, right? So this is important when you particularly have a real world problem, and you know what is the best way to represent that problem in a waveform description, right? For the this is like to understand the physics or to understand the physical interpretation, or to represent the computational state representation. State representation, that is what we called state representation, that is called the quantum encoding part. So this is important. So suppose you have some real world problem and you have a description of the problem by xi and how you represent in the computational basis states, right? Xi in terms of, sorry, what happened? So Q, yeah. So how you represent this particular thing on the circuits, right? So these are like qubits, say Q0, Q1, Q2, right? So on up to Qn minus 1. So these are your quantum registers, and each register you start with computational state 0, for example, right? So what is your initial state? Initial state is if you have n number of qubits, so initial state is so tensor product of all these basis states, right? 0, 0, 0. So all 0 is basically individual particular 0 is 1, 0. So you need to do tensor product of or Kronecker product of n number of such gate 0, right? So now then how you basically encode this problem as a circuit, right? So this is one of the basically problem, how you map your real world problem on a quantum computer, right? First, we need to think that point, right? Representing a quantum information in on a quantum machine, right? So we'll come to this part. Now, once you prepare that particular state, get say the discrete representation is get psi, this one. So you do something here such that this particular state is get psi, right? Now, the next part by what quantum postulate says is that there is something called the time evolution, right? By following the Schrodinger equation, if it is an isolated quantum system, is that the evolution is given by psi t equals to e to the power I h t psi 0, right? This is your time evolution part. And this is this particular equation, if H is Hermitian matrix, then that means H dagger equals to H or H star equals to H, just representation, okay? So then this e to the power minus IHT is just a unitary matrix. And we often represent this by u equals to e to the power minus IHT, because u dagger u equals to identity matrix equals to u dagger, right? You just put h in terms of h. So because h has the property this thing, so you can easily check, just define u and u star and multiply, it will give identity matrix. Okay. So that means whatever we try to do here, sorry. So whatever we try to do here after this state, once we define the problem, suppose we want to find out the frequency component of a signal, or something, just to find out periodicity or whatever, like what information you used to extract out of this chai, or what is the time evolution of this chai. So that means we need any operation we want to do on top of this wave function, that should be a unitary matrix U, right? This one. So that is the any quantum operation you want to do, that has to be unitary, right? Now let us go slowly what this unitary matrix means and all various properties. Then your evolution, after this state. Sorry. After this state, whatever I get, say this is a psi prime, right? And that is basically psi prime equals to u get psi, right? So now we have to learn how to design this U and all various properties. So these things will be coming in the picture of quantum computing when you will try to design an algorithm, right? So basically, you create superpositions, you create entanglement, all these things, right? So those are various kind of mathematical operations, right? And the composite form of all those mathematical operations together will be a unitary matrix representations in general, right? And to prepare this U, we need a Hermitian matrix H, right? If that is the, that basically describe the dynamics of the system, right? So now let us go back to little bit again to the algebra side, and let us understand little bit more, okay, on the computational thing. So computational basis or computational basis states, for a single qubit, we just learned that k0 equals to 10 and k1 equals to 0 1, right? So now if we have multiple qubits, right? Say for example, we have a circuit we want to design, and say Q0 and Q2, these are the two quantum registers, right? And what are the values it can take? It can take any value, 0 and 1, right? And create superposition between 0 and 1. It can also take any value between 0 and 1 and superposition and 1 and 0 and 1, right? So what are the total possibilities? Total possibilities are 0 0, 0 1 1 0 and 1 1, right? These are the four possible combinations I can do using the superposition principle. That is how the quantum computer gives power. If you have n qubits, so theoretically you can create 2 to the power n basis states, right? And that is huge using the superposition principle, right? So so basically for n equals to 2, my computational states will be, basis states will be 0 0 0 1 1 0 and 1 1, right? So to represent quantum information for two qubit system, I will require this particular four basis states, right? Now let's take an example, the Bell state, right? So the Bell state uh, is defined as 1 by square root 2 0 0 plus 1 1. One important thing is to get a Bell state, you need at least two qubits. 2 qubits are required to prepare a Bell state. At least 2 qubits are required to prepare a Bell state, right? Now, how to create the Bell state and all, maybe I'll come later, but okay. So at least let me give an example to get motivation or why we study linear algebra and all this stuff. Okay, so let's start 0, 0. Okay, and suppose you apply Hadamard here. What Hadamard does? What is the definition of Hadamard? Hadamard is a matrix, unitary matrix, and the definition is 1 by square root 2, 1, 1, 1 minus 1. Right? So if I apply a Hadamard here, so what is the state here? The state here is plus state. If I apply a Hadamard in front of a 0 qubit, I'll get a plus state. And the plus state is basically 0 plus 1 by square root 2. Okay. So this is called a superposition state or the plus state, right? So now, so what is the state here? So the state is here, the plus state, tensor product with 0, right? So what then? What are the things I can get? 1 by square root 2, this 0 plus 1 and 0. So 1 by square root 2, 0, 0 plus 1, 0. So this is the state after this. This is a composite quantum system. First, on the first quantum register, I applied a Hadamard, right? Second quantum register, I did nothing, right? So then what is the overall quantum representation, right? After applying the Hadamard on the first qubit, the overall representation is 0, 0, 1, 0, right? This is just a normalization factor because all the quantum state are normalized unit vector, right? So the next part is just apply a entangled gate or a CNOT gate here. So the state here is plus tensor product with 0. I'm removing this plus here, okay? Just to remove the confusion. Now, the definition of CNOT is in the matrix form. In the matrix form, the CNOT is 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. So if you look at this particular matrix quite closely, you will see that first part of the matrix is basically it is an identity matrix, right? And second part of the diagonal part is an Pauli X matrix, right? So that's why C naught can also be rewritten as 0, 0 outer product, tensor product with identity plus 1, 1 outer product, tensor product with X, Pauli X. Okay, this is X means basically 0, 1, 1, 0. This is the definition of Pauli X matrix. Pauli X matrix. Why it is called X matrix? I'll come later. Okay. So if that is the case, 0, 0 identity plus 1, 1 X, third and fourth. Okay, sir, please share this whiteboard presentation. Sure, sure. I have all the notes I'll be sharing. Don't worry. And also I'll be sharing the notes. Yeah. So basically, this okay. This is tensor product representation. This is in latex we called O times. Okay. This is a Kronecker product or the tensor product. This is X. X means this is Pauli X. For clarity, I am writing as sigma X. Okay. So that means sigma. Sometimes we write sigma X. Sometimes also we write X. This is called Pauli X matrix. Okay. And the definition is 0 and 1, 0. This is basically 90-degree rotation matrix. Okay. So if I apply the C naught here, what it is doing? This is a matrix basically, right? It is a matrix, and you already have a matrix here, right? So this matrix times this matrix multiplications, right? But what we have done already, you have multiplied this particular, this is a vector. You have already multiplied this vector with this matrix. So that means you already have one vector here. So you just need to multiply this matrix times this vector. So if you have any confusions, so let me clarify again. So this 0 and 0, this 0 is what? This 0 is basically 1, 0, right? For full clarity, this is 1, 0. So if you do a tensor product of these two things, so what you will get? You will get 4 cross 1 vector. Okay. You have a 4 cross 1 vector. Now you have to do something, and that something will be a 4 cross 4 matrix, right? I mean, in order to get this multiplication done, right? So now this is like how many rows are there? There are 2 rows, 1 column, 4 rows, 1 column. Correct. So basically, okay, the multiplication happens this way. Okay, we are representing this way, but you need to compute right to left. Okay, so 4 cross 4, then this, right? So that's what we do, right? If you have a system, sorry, if you have a system X and it passes through the if you have a signal X passes through a system A, then output Y equals to AX, right? This is how we write, right? So similarly, your quantum operation, this matrix come first and then this vector. So it's a 4 cross 4. And these first 4, how you prepared, this is you have just applied a Hadamard here, and you have done nothing, means there is an identity operator, identity matrix, right? Clear? Now you are applying a C0 gate here. And the C0 representation is just this way. So the mathematics part is fine. Mathematics is basically I cross I, 0, 0, 0 outer product, tensor product with I, plus 1, 1 tensor product with X, right? This is the definition of C0. And what was my state here? My state here was this one, right? So 0, 0 and 1, 0. So here my state is 0, 0 plus 1, 0. Forget about the normalization factor 1 by square root 2. Now I need to basically multiply these things with this. You don't need to do anything. You just what there is, the philosophy is, if you apply C0 gate or C0 matrix on a circuit, if there is multiple qubits, okay, and you are just applying the C0, it's a 2 qubit gate. That means between 2 qubits. Here they are simply Q0 and Q1. These are the 2 quantum registers, for example, right? So you are just applying between 2 qubits. If the first qubit is 0, it does nothing to the second qubit. If the first qubit is 1, it flips the second qubit. That is the philosophy. So what it does, the output will be, forget about the normalization factor. If the first qubit is 0, it does nothing to the second qubit. If the first qubit is 1, it flips the second qubit, it becomes 0, becomes 1. Right? This is particularly, if you normalize these things, this is called the Bell state. Okay. And maybe sometimes later we can have a program, Qiskit program, to see visualize this thing. So what you have done initially, you could prepare, suppose your information has like 2 qubits, Q0 and Q1. That means all the, if you could apply Hadamard both side, right? So what are the possibility? All has the 1/4 probability of this 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 computational basis states, and all 4 might have the probability 1/4. Theoretically, computationally, there can be some little bit more or less due to measurement and decoherence and other things. So 1/4 should be the error. But just by creating the this Bell state, what you have done, you just maximize the probability of this 0, 0 and 1, 1 state, right, to half probability, 1/2 probability each. theoretically, and you removed the probability of occurrence for these two particular bases, right? This is the beauty of this thing, just by doing simply matrix multiplications, right? Any questions so far? Okay, so now there is something called the Walsh-Hadamard basis transform. Okay, not clear. Okay, so please you may ask me question if you have any issue, or if you feel difficulty something.
So participants, if you have any question, you may put it in the chat box
Yeah,
while having
please.
discussion. Sir will address whenever sir feel, you
Yeah,
know.
sure,
So
sure.
so one question someone has.
Yeah, yeah. So how we are dropping these two states? Yeah. So you created so basically how we created those things. So Q0 and Q1, right? And we applied so first qubit, on the first qubit you applied the Hadamard, and to the second qubit you did nothing, right? This is an intelligent way of designing circuits, quantum circuits. We'll learn much clearer of this topic in a quantum computing paper next in QT-05. But because I'm covering the algebra, so I'm bringing some notion of these things here. So basically you have done nothing means there is an identity matrix, right? So now we apply the C naught here. The purpose, so what is the state I created here? The state I created here is 00 plus 01. This is what I have, sorry, 10. 10. These states I have created just by, you just need to do, I think some little bit of the tensor product thing, right? Um, so just then when you apply the C naught here, and the purpose of C naught is basically, if you just simply if you wish, you can just simply do this matrix times this vector that we just generated, right? Which was the vector, this one. Just by hand calculation also you can do this. But the trick is, if you just don't want to do a 4x4 matrix multiplication, matrix vector multiplication, the thing is this will be 0 0 because the first vector is 0, so it will do nothing in the second qubit. But if the first quantum register is in 1, then it flips the second qubit. Basically, it will become 1. 0 will become 1. So now if you measure on this particular quantum state, right? This psi 1 by square root 2, 0 0 plus 1 1. So there is no possibility of the other two states. Otherwise, unless otherwise there is hardware inaccuracies and other things. But in general, theoretically, so there are only two possibilities: 0 0 and 1 1. So if you do the mathematical projections, right? So you'll get only these two particular basis states and the equivalent probability 0.5 theoretically, right? Yeah. So so basically, what we will be doing is, there are three part in most of the quantum algorithms or quantum computing algorithms. First we need to do encoding. Okay, first we need to do encoding, means creating a vector ket y, right? Or ket psi, whatever symbol you wish to do. It's a vector, simply a column vector. What are the properties? It's a column vector. It's a normalized column vector. Normalized column vector. Coefficients may be complex. And basically we take all these things just to obey all the probability formula, because the sum of all the coefficients would be equals to unit, right? Unity 1. So this is the first step. Then you need to create evolution, or sometimes called simulation. right? Or sometimes people call it as just a system representation, right? In quantum, sometimes people call it quantum circuits, although you need to have quantum circuits here, quantum circuits for uh, particular applications that you are doing. Then once you just apply these things on top of this, suppose this is your some quantum circuit, say f, and whatever you get output, right, at this particular thing, suppose you get z as your next state or evolved state, right? So we do quantum measurement. So you get the probability of the various computational basis states here. So what are the probabilities to get these things? So now f can be, if it is a Fourier transform in quantum, it has equivalence like QFT quantum Fourier transform, right? So then basically you write get z equals to QFT is basically it's a DFT matrix, and the implementation is done on the quantum device. So basically the elements we know, right? 1 omega omega square, so on, right? 1 omega square omega to the power 3 and so on. So it's a n cross n DFT matrix, right? So basically QFT times this get y, right? This is how we represent it. Now, say for example, if you want to do Walsh-Hadamard transform, so you need to create a quantum circuit, which is quite easy here, such that this particular thing f is your f matrix will be um, 1 by so it is maybe 1 by 2 to the power n, you can write um, h 2 to the power n minus 1, h 2 to the power n minus 1, h 2 to the power n minus 1 minus h 2 to the power n minus 1, where h1 equals to 1, okay, and h2 equals to 1 1 1 minus 1. So it's just a recursive representation of the matrix by 1 by square root 2. This is just a normalization thing. So you can recursively create this kind of circuit for Walsh-Hadamard transform. Just this is your simple Hadamard gate, right? And this is just H1 by definition. So for example, you can create this kind of for various image classification and all those kind of problem, 1 1 1 minus 1 1 1 1 minus 1 1 1 1 minus 1 minus 1 minus 1 minus 1 plus 1. So this can be your 4 cross 4 F matrix. And can you create a quantum circuit for these things? Then simply by encoding an image in the initial state, you apply the Walsh-Hadamard transform and you can see what are the features, right? So this is how that is why actually matrix vector multiplication is so important here, right? And I'll pause here for just this video recording thing, and I'll come back on some advanced things. Yeah. And if you have any question, you can write it on the chat box.
Okay, so meanwhile, you may all the participants, I request you all to go through the previous topic, means whatever content sir has discussed, and compile some doubt if you encounter. So put it in the chat box. Sir will address it after joining back.
Sure. Okay, shall I resume? Like, shall I start?
Yes, sir, we may start. Participants are already there.
Yeah,
So
sure.
we'll
Thanks.
continue with that.
Yeah.
Thank you,
So,
sir.
I believe that some of the candidate might also new in this course, so they may face difficulty with tensor product. So let me quickly recap tensor product. And of course, tomorrow I'll be taking 3 hour session. So matrix factorizations, various algorithms, their complexity I'll discuss in details. But for today, I'm just also taking some of the basics things again. Um, Tensor product. So this is very very important in this context of quantum computation or quantum technology. And the notion why it is related, because um, so suppose you have two quantum particle or two quantum phenomena, right? In typically when belongs to quantum computing, we say two quantum registers, right? Q0 and Q1, right? And whatever this Q0 and Q1 how you are creating. So basically, um, this Q particular quantum register, right? There is a oscillator. For example, if it is a superconducting thing, something like you have a LC oscillator, say for example, right? So this is your L and this is your C, right? And using this LC oscillator in the cryogen in the actual setup, right? You are creating this kind of energy distribution plot. So let me just 1 minute. Sometimes create problems. Yeah. So what happens is you create this kind of energy distribution plot. Suppose this is your ground state and this is your suppose the first excited state, and then there are multiple energy states, right? And in the below levels, so typically we take the first ground state, we take the ground state as the first qubit or the zero qubit, kate 0, and the second one is the first excited one as a kate 1 to represent our informations, right? And then basically so you take this is just for a one qubit, one a particular superconducting qubit, right? And suppose you have another LC oscillator, right? C and L, right? And you for the second qubit also, you have a energy representation like this, right? This 0 and this 1, right? And suppose to create this thing, right, as an artificial atom, basically this oscillator behaves as like that. And then we typically, when we place this first, say, suppose this LC is represented by this way and this another LC is this way. And when we talk about the mathematical representation of this entire system, right, this is called a composite system, right? So because any operations you are doing, so one is the hardware part and one is the software part, or typically we say the mathematical part, right? Or the logical part, right? So this is giving you something ket 0 and ket 1, right? The combination, superposition, and anything. These are the computational basis states, and here it is also 0 and 1. These two are the basically computational basis states. But when we write it in the system together, right, it forms the composite basically quantum system, and the possibilities are 0 0 0 1 1 0 and 1 1, right? These are four computational basis states how we create, right, using the superposition phenomena, right? So now so in mathematics, typically we denote this by the mathematical operation called tensor product, and this is defined both for vectors, matrices, or any tensor, general quantity tensors. So suppose you have two matrices in general, say the matrices are A and B, these are two matrices, right? Okay, by the way, any operation you do on the, suppose you apply a X gate on gate 0, right? Poly X. So that means a rotation 0, 1, 1, 0 matrix times the vector 1, 0. This and this are same thing, right? So it will become this just simply if you do these things, you will get 0, 1, right? That means if you apply X gate on gate 0, you will get gate 1. If you apply X on gate 1, you will get gate 0. This is why it is called the NOT gate in quantum computing, right? Pauli not gate or simply not gate in quantum computing, right? It just flip the logic, right? There is one extra term that is the phase factor, phase flip, and that I'll come later sometime in the quantum information chapter, not here. Okay, so now you can see this. Um, so these kind of operations you do here on the mathematical thing, but in the physical hardware, um, typically you apply a pulse signal here, microwave pulses, right? To create this kind of operations, right? But this is not same as the like you do in the digital logics or the classical circuits like CMOS technology and all. There you typically create this kind of things, right? PMOS and NMOS thing. So and here it's some VCC. Here is some VDD, right? Ground state and all. And typically they might be connected. Here is some, you give high voltage or low voltage depending on that, you will be getting something here as a 0 and 1. So this is like you create this is your logical representation of NOT gate in classical logic, right? But in quantum hardware it's some pulse signals, right? So this is the hardware part, and this is the logical part. Now typically we can talk about the states, or you can talk about the operations. But in both the case, the important thing is if you have multiple such quantum systems, you need the help of tensor product as a mathematical tool, right? Now, if you have two operators, A and B, the tensor product of A and B is written as, suppose the matrix element of A is A11, A12, right? So on, right? And this is A21, A22, and so on. And this is ANN. There are many such elements, right? And B might have similar B11, B12, so on. So if you do tensor product of A and B, so it will be A11 times the entire matrix B, A12 times the entire matrix B, and so on. A21 times matrix B, A22 times B, and so on up to ANN, N maybe capital NN times B. So this is the tensor product definition, right? And let's take some example to understand. Okay. To understand this part better, uh, then in bottom part of the screen is not visible, is it? Um, uh, is this clear now? Can see this, right? Okay. So let's take two vectors, v equals to 1 and 2. And let's take another vector, w equals to 3 and 4. Okay. Vectors are also matrices. Okay. So this is 2 cross 1 matrix. And this is another 2 cross 1, right? 2 rows and 1 column, right? So basically all these columns of a matrix, they are vectors, right? Column vectors. So just take any two particular column and just name them as v and w. Now let's do the tensor product, right? V tensor product w equals to, by definition, sorry, by definition it is 1 2 tensor product 3 4, right? So 1 times 3, 1 times 4, 1 times 2 times 3, 2 times 4, right? Just simply define this way. Or uh, I hope it is not that difficult, right? And the answer is 3 4 6 and 8, right? So this is how you create a 2 cross 1 to 4 cross 1 by using just two simply qubits, right? So you can take three, so two quantum state, and you can create this dimension this way, right? That's how if you have 100 qubits, right? And it is so powerful, 2 to the power 100 computational basis states to represent your system. So just for comparison, I can tell you how powerful it is. The direct comparison I shouldn't do, but in general, this is for simplicity. If you have a present your supercomputers, right, HPC, best HPC, and it has a one exaflop speed right now, right? Exaflop means this is basically equivalent to 10 to the power 18 operations per seconds in your best supercomputer on Earth, operations per second. And here you represent your numbers in the decimal systems, but if you do represent in the binary twice bitwise representation, it's equivalent to 2 to the power 60, right? Representation. So that means you can seamlessly do 2 to the power 60 operations per second on a best non-classical HPC high performance computer or the supercomputer, right? But if you have a problem which is just greater than 60, say 80, you want 80 to the power 80 operations, right? Operations per second for some application, maybe femtochemistry application, autochemistry applications, biomolecular simulations, quantum finance, these kind of things. Then you can realize HPC is not enough, right? Alone is not enough. So basically, then you only need 80 80 good quality qubits, because only 80 qubits is very different from 80 bits, because it can create 2 to the power 80 computational basis state. That means so powerful using this property, okay, superposition property. Let me give you one work, and I will wait to see who gives the answer first. So 1, 2, 3, 4. This is your first matrix, and second one is 0, 5, and 6 and 7, right? Let me know what is the A tensor product with B, right? So 1 minute time, okay. Please do not use calculator, just do by hand, right? It won't take much time. Just put in definition, you will get the answer. Question number 1. Question number 2. What is the tensor product of 0 and 1? Question number 3. What is the tensor product of superposition gate and superposition gate, Hadamard gate and Hadamard gate? Right? 3 questions. What is the output state, right? Because you all are profs in your college, so you can create these kind of nice questions for your students, right? For teaching examinations. These kind of questions are often asked even in the interview questions. Okay. I mean, in industry interview questions also. So these are so easy because this is exactly what is called, we call basics. Okay. So x, the definition of x is basically 0, 1, 1, 0, and z is basically 1 minus 1, 0, 0, right? So this part will be the tensor product, right? And you will get a 4 cross 4 matrix. Here you need to do tensor product. You will get 4 cross 1 vector, and you need to just multiply 4 cross 4 matrix with a 4 cross 1 vector, and you need to give me answer of 4 cross 1 vector here, right? These are questions just I am just trying to make just now. Okay, I'm not copying from anywhere. Okay, so that you will get a sense how to create circuits and all. Okay. I'll wait for 1 minute and then I'll go for another topic. Just an application um, of this to find the quantum fidelity circuit. Yes, thanks. Somebody answered the question. It um, correct or wrong, that's the different thing, but at least you have tried. Appreciate for that. Okay, thanks. So the answers are already there in my notes, so you can have a look there after completing this course. Yeah. So now we'll learn about one particular circuit called the swap test circuit or the quantum correlation circuit. Or so this is also known as the fidelity circuit. And this is so useful, just using this basic concept just we learned now. Okay, and this is a extremely useful quantum circuit. Okay, those who talks about quantum machine learning and all, so this is a very frequently used circuit in quantum machine learning and many other stuff in quantum chemistry and other places. Okay. um so what is this circuit, or what is the motivation for this circuit? Suppose okay, so first of all, um if you have two quantum states, right, ket psi and ket phi, right, and you want to identify what is the correlation, right, or what is this particular state, psi and phi inner product, what is the answer of this, right? Or you may find the distance between these two particular thing, right, psi and phi square, right? You may have these things, psi and phi square of this, right? And this is basically called L2 norm, right? And L2 norm is so common in machine learning literature, right? And many other places. So those who study kernel, right? Kernel metrics and all, you need to do the dot product between two feature vector and take the square, right? L2 norm distance, right? Also, you got some answer, say you did an experiment and you got some quantum approximate quantum state get psi prime, but actually it should be, or theoretically it has to be phi, but what you got actually is phi prime, and you need to check whether the dot product between phi prime and phi is coming closer to one or not, right? And this is called the fidelity check, right, of an experiment, right? So these are several questions related to the single circuit called quantum swap test circuit or the fidelity circuit. Okay, and we'll learn this circuit now. Okay, using the basics operation we just learned today. So the circuit is something like this. If you have pen and paper, I'll suggest you to draw with me and do the calculations with me. Okay, and draw the circuit, not a small box. Take the left to right entire page to draw this circuit. Okay, like this. So we'll be taking three quantum register. One is get 0 initialized with 0. One will initialize with phi, and one will initialize with state psi. Okay, and you apply Hadamard in the first qubit. You did nothing in the second and third. Then we apply a controlled swap gate. It looks like this. Control swap gates. It is known as C swap. C swap gate. Okay. This is Hadamard gate. Okay. Those who don't know what is swap gate, let me define what is swap gate. Just 1 minute. So swap gate is defined as 1 0 0 0 0 0 1 0 0 1 0 0 0 0 0 1. So if you look at, there are four parts, right? So there is kind of this row change, right? Something like this here. There is something, if you compare it with the identity matrix, that is 1 1 1 1. Now this one and this one, there is a rotation kind of thing, place change, right? And it exactly what it does is basically, if you have zero, basically it's a 4x4 matrix. That means it requires at least 2 qubit operations, right? Or a 2 qubit gate operations. And if you C swap is just a 8x8 controlled swap. I'll come how it does and all. But in general, if you have an information here and here, and if you apply a swap gate like this, so if you have X here, Y here, then it will be X and it will be Y. Okay. After swap operation. Right? This is the purpose of this particular quantum operations. Okay. And control swap is it depends on what is the initial qubit, 0 or 1, right? So I'll show how it does. Okay, how it works. Instead of matrix definition, that's just a C swap is just a C swap is just a 8x8 matrix. Okay. So you will have something like all 1, and some places it will be 1 0 here and 1, something like this. Okay. So let's instead of remembering things, let's implement the things and understand how it works. So then in the first qubit there will be 1 Hadamard here, and you do nothing in the second qubit and third qubit, and then you do a measurement, right? Okay. So we'll go slow by slow. Suppose this is my step 1. Suppose this is my step 2. This is my step 3. This is my step 4, and this is my step 5. Last one. Suppose this is step 1, step 2, step 3, step 4, and after measurement step 5, right? Before measurement and after measurement. So so I need to scroll to write it, but in your paper, if you have time, you look at the circuit and see the calculations, right? So initial step 1, we did nothing. What was our state? Our state was 0. Our state was psi, and our state was phi, right? Something like this. Or better, I should write this psi phi. That means the circuit here. I should. Sorry. Mm, mm. It's creating some issue. Please give me 1 second. Yeah. So if I write that way, that means so now I have three registers, 0, psi, and phi. And if they are together, I need to do tensor product between them, right? This is my first step. I won't do anything above this. So now the thing is, the step 2, what I'm doing is on the first qubit, I applied a hard amount, right? Here I applied a hard amount and I have done nothing, means identity and identity, right? So then what will be my state? This particular 0 will be 1 by square root 2, 0 plus 1, tensor product psi and tensor product phi, right? Step 3. So this particular step is here, right? Here, step 2. Now step 3, I already have applied. I applied the C swap, controlled swap gate, right? So if it is controlled swap, then what are the consequence? So first, I am keeping this 1 by square root 2 normalization factor outside, right? And before applying this, just breaking the steps, right? So that is 0, psi, and phi plus 1, psi, and phi. These are the two steps before swap, right? So these two are equivalent, so I can erase this thing, and I can write step 3 here. So I apply the C swap gate, right? C swap means I have to look if the first qubit is 0, it does nothing. If the first qubit is 1, it swaps the quantum informations, right? So what it will happen is 1 by square root 2. First will be 0, psi, phi. I have written nothing means there is a tensor product, right? Plus 1, this will be phi and psi. Phi will come here and psi will come here. So this is the purpose of C swap, right? Now in the fourth step, what I have to do? Fourth step, again I applied Hadamard in the first qubit, right? So, so first qubit, if I apply that, so what will happen? 1 by square root 2, then this 0 will become 0 plus 1, right? This 0 will be, if I apply Hadamard, so this will become plus state, and this will become minus state, okay? So plus state means 1 by square root 2, 0 plus 1, right? And minus state means 1 by square root 2, 0 minus 1. These two are the implications because this is the first register, right? Okay, those here. So I got some informations here, right? And just because I applied a controlled swap, right? So the information, the psi and phi swapped, conditioning where what is the state here, right? Depending whether it is 0 or 1. So whatever I got, then I will apply again a Hadamard. Then all the first registers, 0 will become the plus state and 1 will become the minus state, right? So here I am calculating here. So then this that means what is happening? See, this 0 will become 1 by square root 2, 0 plus 1. This psi and phi will be intact, right? Plus 1 by square root 2, 0 minus 1. Um, mm, this is not needed. This bracket is unnecessary. Uh, it will be phi and psi, right? Any question till now? This is I'm just doing the derivations, right? And now this bracket is for this one, right? So now this 1 by square root 2 and 1 by square root 2 will become half, right? just if you do multiplications, and if you put all 0 in one place and all 1 in other place, just by breaking these equations, like 1 times phi psi, 0 times psi phi, and 1 times psi phi. Similarly, 0 times phi psi and 1 times phi psi. So it's doing a lot of trouble, this screen, digital screen. Yeah. So then what I'll get, something like this: 0 tensor product with psi phi plus phi psi plus 1 tensor product with psi phi minus phi psi. Step 3 is tensor product. Yeah. So I mean, I just omitted, if I am writing these three things. So there is the tensor product. So I have written nothing means tensor product. So typically what happens, the convention is, if you have 0, 0, 0, say as a tensor product, right? So you can write this way. You can also write this way. You can also write what I haven't written here as 0, 0, 0. Same thing. These three things are the same way of representing information, right? Um, yeah. So here, step 3 to 4, again I applied Hadamard, right? So this 0 becomes 0 plus 1, and this 1 becomes 0 minus 1, and the other states are kept as it is, right? This part and this part same. This part and this part is same. Just 0 becomes 0 plus 1, 1 becomes 0 minus 1. That's all. Okay. Now, now this is my overall states, right? Now, initially, what we have learned, if you want to do quantum measurement, right? So you got something where you have the product psi and phi, phi and psi, right? And typically what we do, by doing measurement, so if you want to do measurement to get the probability of the computational basis states 0, so what is the answer? So basically dot product between 0 and this particular state, suppose this is ket psi, right? So you want to calculate this square, right? This is the probability of getting the quantum state psi in the computational basis 0, right? This is your probability. If you want to calculate this, so this part will become 0, right? Because this computational basis 0 and times 1, it will be basically 0, and this 0 times 0, this particular thing will be 1. So basically your answer will be um, half of 1 plus psi and phi square. Okay. And probability of getting 1 in the computational basis 1 will be half of 1 minus psi and phi square. Now you can ask me where this square is coming, because you need to do square. So after doing the dot product, right? This part for 0, this part is cancelled. Second part is cancelled. This part is cancelled for 0, projecting on 0. So you have only this part, and then you have to take square of this. If you take square of this, so basically you'll be getting something like this, because the dot product between the same product will become 1, right? And the opposite part will be coming as side. So basically, okay, let me expand this equation for simplicity. Let's not keep anything doubt. Okay. Say, let us calculate the probability of 0. So 0 times psi means entire state. So you'll be getting 0 times this 0 plus psi phi plus phi and psi, right? I'm not writing the second part because ultimately that will come as 0 times 1 means 0, right? So plus 0, I'm writing plus 0. Okay, that is not required. So then this 0 times 0 will become 1, right? And then I just need to calculate this part, right? So, and then take square of this, right? So what will happen if I do the square of this to calculate the probability? What are the terms coming? So the first term, it will be uh, s- so basically this, I shouldn't write this way. This, because it's a complex quantity, star this, right? Plus the second term will be pi psi star pi psi, right? So basically this times this star, this star, and the alternate product means this times this, right? So just plus another term, right? So you will see that this and this together it will come here, right? And another term will come as basically so one term will become one, and two terms together will be this one square term, right? So just break this two part, and there is one half. So just by expanding these equations, you will be getting this, because outside there is one half. So basically it will come something like this. So if you break this equation, it will be coming as 1 plus 1 plus something like this, phi and psi square, right? And outside there is another half. So it will be 1 plus 1 will become 2 pi and psi square divided by half. So it will become 1 plus this thing, right? So just a 2-3 lines calculations. So there are lots of tutorial online also. You just need to do quantum swap test. Okay, swap test circuit, and best you do by hand calculations. Else you just do a search and see all the detailed steps, right? Just to verify your calculations are correct or not. So by this you can calculate the correlations, right? And if you have a real world problem, say for example, um, yeah, you have an apple, right? And you have an orange, right? So, and this apple is somehow you created a vector A, and A vector, and for orange you have created O vector, right? And you want to calculate the similarity between uh, orange and apple, right? This thing. Sometimes this classification problem, you can see if they are closely related to one, so you can classify into the same class, and if that is very largely deviated, you can say these two are different class, right? Something like that. So there are algorithm like the support. So Dr. Anupama will be teaching these things, so I'm not covering this part, but these are just basics. Okay. Um, well, so now let me cover maybe something called the mathematical projections. And tomorrow onwards, I'll be going for some matrix factorizations and numerical methods, how to compute those things. Okay, even without going much in the theory portions, let me do something. Let me introduce some programming stuff today, because we have about 10 minutes. So please allow me just 1 minute for the screen change part. Tomorrow I'll be sharing all the notes, so don't worry for that. Um, is this visible to everyone?
Yes, sir, it is visual, sir.
Okay. So let me show some experimental stuff. Suppose, okay, so don't worry about these packages and all. These are very standard packages. Okay, so okay, so this NumPy is a package in Python for numerical computation. Matplotlib is similar to MATLAB, so basically to help you get some plots. SciPy is basically one scientific library from Python just to help you to get various scientific calculations like matrix inversion, etc. In Python. Such a example, I call this linear algebra package from the SciPy library, right, from Python. And I took a certain number of Qiskit packages. So this is very standard like Qiskit circuit, this Qiskit info and Qiskit visualizations, right? I'll be sharing the code, don't worry. So let's take all this library for simplicity. Now, suppose let's visualize a vector v equals to np dot array. And array, basically one dimensional array means a vector. Okay. So I take 2 cross 1 as a vector. Okay. This is my vector. And if you type np, okay, type, let's check v. It's a ND array, NumPy array. Okay. So now suppose let's I call this matplot library as plt. So plt dot plot, like MATLAB you do simply plot, right? So plot this plt dot plot, suppose this v, right? And let's check. So it's now is simply something like this, right? But we can represent from the origin, this particular vector 2 cross 1 from origin, right? Let me show you all the plots and discuss slowly. Suppose this way, you define a vector v, right? And we just create a figure, plt dot figure, and we plot both way, just direct plot wise and scatter plot wise things. So we'll do two things. One is the just directly plotting this 2D vector, that 2 comma 1 means x-axis 2 unit and y-axis 1 unit. And then we'll do a mathematical projection on the x-axis. Okay, and we'll see that. Okay, so just we do the dot product. Similarly on quantum you can do the swap test circuit. So and in simply classically we do np dot dot, so u dot v, and then we normalize this, right, just to get it normalized vector. Okay, because that's the definition of the projection, right? So if you plot these things, so what we'll get is the original vector u is something like this u. Okay, and v is the another vector, this one, the green one, right? And when you project this u vector on the space, this green one, so this is the projected part here, right? And this blue dot is basically the projector operator, and you can see it's a unit, basically projector here. It is as a normalized one, right? So this blue part in this green as a projector shown here, right? So similarly, there is something called the reflection operator, right? So why I am telling all this stuff? So suppose you have a qubit and you want to rotate it along the x-axis, y-axis of certain angle or twice of the certain angle, especially when you basically apply the Grover search algorithm, for example, right? So you do iterative reflections, left hand side, right hand side, right? So you need to design a quantum operations such that you can do this kind of operations, projections or the reflections, right? So it's a projections means just projecting on the computational basis states or some other vector v, right? Here reflection is just twice of this projections minus u, and we can see this. So if this is the original line, right, and this is the mirror of reflection, so you get from this red to blue, just 90-degree rotations, right? Here in this particular case, but you can change the reflection. So just it's simply like if you have a plane of mirror, right? And the angle from the mirror plane to the particular vector will be same as the reflection angle, right? Incident angle equals to the reflection angle. Just the light experiment we did in childhood, right? So and you can change the theta. Say for example, here we have taken np dot pi. So by 445 degree, you can take say 360 degree, for example. And so here the point of the reflection changed, right? Um, so so basically, so reflection I'll define formally for various decomposition techniques. And next day although I'll be sharing the codes, but we'll cover the theory portion of QR decomposition, Cholesky decompositions, EVD and SBD tomorrow. And not just the theory part, but their relevance to the quantum computing part, and why basically we decompose a matrix into the diagonal form. If a particular matrix is just ordinary, if it is symmetric, if it is positive semi-definite, then what are the consequences of its eigenvalues? What is the complexity reduction I could do? So those aspects I'll discuss tomorrow. And this is a Bloss representations, right? Okay. So we took two registers, quantum registers, that is QC equals to quantum circuit 2, right? And the first qubit, okay. So let me, instead of this, let me draw these things, QC dot draw, and then I can do these things. Okay. So is there any question? Let me also check that thing also. Page shared. Please share the code. Sure. Okay. So you see, we call these libraries. Forget about the libraries. What we have done, we took two quantum registers, two, right? Suppose we let us take three quantum registers. Okay. And the first quantum registers, we just applied a Hadamard, right? And the second, suppose let's not do anything in the second, right? Say QC. I won't do anything on the second quantum registers, right? And third quantum registers, suppose um, I apply CX, control NOT gate between 0 and 1, right? Suppose let's create a Bell state, for example. So, yeah. So I apply Hadamard in the first qubit, and then I applied C naught in the 0 and 1. So what is the circuit? Circuit is something like this. I apply the Hadamard in the first, and second I apply just CX gate, right? Then what is the my state vector representation? So right, so you can't see things here because uh, right. So you need something called multi-vector representation, multi-vector representation. So I'll come that later stage. But for now, you can create circuit, right? Tomorrow I'll show some visualizations, but for today, you can create some more circuits. So just we have studied the some circuits, right? That is the quantum swap test circuit, swap test circuit. So how to do these things? So let's try this. So let's take three quantum registers, for example, right? And first quantum registers, we need to apply Hadamard, right? So QC dot H means you are applying the Hadamard on a quantum circuit in the first register. First register start with 0, okay? And then you do not apply in the second and third, nothing, right? uh, but suppose we want to we want to understand the correlation between x and x. So you also take qc dot x in the first qubit, and qc dot say yx in the second qubit. So we just need to calculate the Pauli X state with the Pauli X state, the fidelity. It should be, the answer should be equals to 1, right? Because the second and third registers we have taken x, right? And the first registers we are just starting the applications of this, right? So first you apply Hadamard and then you apply C swap, right? C swap between 0, 1, and 2. And then you apply QC dot this Hadamard in the first qubit, right? This is the circuit, right? So so you see, okay, I made some mistakes. So it should be 1, it should be 2, right? So what I have done, there was nothing. First, all are 0. Then I created the second and third register, that is Q1 and Q2 as XX state. And my objective is to calculate the fidelity of these two states, right? Equals to 1 or not. And my circuit is Hadamard, then C swap and Hadamard, right? Tomorrow, your homework is to calculate the probability, of the first qubit, q equals to 0, right? And let's take the theory with this. With this, I conclude my sessions for today, and I'll come back tomorrow. And if you have any questions, please feel free to ask me. I'm here.
Point दिखा दे. Thank you very much, Dr. Mustafizur sir.
Sir, you joined. Thank you.
Yeah. So yeah, any questions, please? You can write. Yeah, sir will share the Jupyter notebooks. Don't worry about that. Right, code and all is there. Yeah, sir, there are some questions.
Yeah. Can we plot Hadamard state 0 and 1? Yes, so there is something called multi-vector visualizations. Maybe tomorrow, if I get some time, I'll do that. Okay, don't worry. And you also, please, everyone, please, if you are interested, please visit this IBM Qiskit learning platform. Everything is there. So let me share you the latest website link, so that once you go back, you have some time, so you can have a look.
Yeah, this is to register for the newer version of Qiskit. For those who have not joined, you can please take it forward, right?
Yes.
Which question, which answer? Arunima ma'am, can you be elaborate? Please see your answer. Can you write the answer again, maybe? You are on mute, sir. You are on mute. Mustafa sir, not able to hear you. तो वो किसी से बात कर.
Hello.
Yeah. You are on mute actually. Yeah, you are talking to somebody. I think.
Sorry.
You are on mute.
Audible? Sorry.
Yeah. Now you are audible.
Yeah.
What you are saying, we are not able to hear.
Okay, so basically, I during my lecture I gave some questions, and all the
Okay.
answers are there in my notes. You may kindly verify. And if Arunima ma'am is asking about some quiz and all, maybe you can answer. If
Okay.
there's other thing, yeah.
Okay, that must be something.
And those who actually wants to study linear algebra a bit more, maybe they can just 1 minute read this book. This is a very good book. This written by Golub and Loan. Okay, and why I suggest this book has no relation to quantum computing or quantum this physics. This is pure mathematics book, but we deal with eigenvalues, eigenvectors, observable Hermitian matrix, everything, right? And this is a very standard mathematics book for that. I mean, I suggested 3-4 books, but this is one of the. Okay, this is not clearly visible now.
Yeah, matrix computations, fourth edition, Gulab and Lohan.
Yeah.
Lohan. Loan.
Yes.
Charles P. Van Loan.
It's a very good book. And those who are new, maybe they can start with Professor Gilbert's lecture series, and he has also books, so you can start with that. Yeah, I think I took a lot time, and thank you for your patience, very kind patience, because you are already teaching in your colleges and then managing time to listen to us. So thanks a lot.
No. Yeah, I would also like to inform that recently Mustafizur sir had published in Nature Scientific Report. So that's a journal publication which is very high standard. So shallow entangled circuit for quantum time series prediction. It was published in Nature. Nature means top #1 journal in the world.
Thank you.
So he has published, and that too as a first author, as a research scientist. So that's excellent. So we are very happy and proud that we have somebody as qualified and as excellent as Dr. Mustafizur to share not actually on full quantum, but actually on the mathematics part of quantum, and always he chooses this part. Actually, he can do very well in Qiskit and other things, but then this, if the strength of mathematics comes into the course, then he feels that this can be there. Yeah. Thank you so much, Mustafa sir. Please note, tomorrow there will be 3 hour lecture. So I think already Vikas ji has announced. Announce nahi kare kya? So tomorrow there are 3 hour lectures. So our session starts at 2 p.m. tomorrow.
Right.
So please note this point. That is to give you more detailed session of Mustafa sir. We expanded that. So we are meeting on 29 days and covering 60 hours.
Yeah.
So Mustafizur sir will be covering 5 hours this week and 5 hours next week. So next Saturday also we'll have 3 hours.
Yeah.
So 2 to 5 p.m. So please be prepared in that sense. We'll send reminders, but please set a reminder now itself that 1:30 Mustafizur sir class at 2 o'clock. So please be available. We'll take a break in between tomorrow and for 10-15 minutes, and then again we'll continue. So so we'll hope that there are no more questions. So the title is copied there. Please don't ask for soft copies. Soft copy sharing is not the right thing. You can share if somebody has. You can share personally, one-on-one. You can try to get it. I don't mind if you use it. I don't say don't use it, but don't share it on the groups. Don't share it in the public forum. It's not ethical. That's what I would feel. Of course, I understand. But if there is a requirement, please share and manage. But I would say that we should respect the authors also. I am an author, so I understand the pain sometimes. So you can think about that. But yeah, the books are available. You can very easily get it. So just try it at your level and then do it. Of course, everybody is doing so. But I would personally feel that let's not use our WhatsApp groups and these things to share the content. Sometime earlier we had shared one folder of all the books. We have shared somebody shared the folder. So maybe sometime later towards the end of this course QT-03, I will share one folder by somebody. I will request them to share the folder. They will share it and then you can follow it. So we'll meet tomorrow at 2 o'clock, and then quiz is available. Quiz cover. So participants, I request you all to kindly convey this information, whoever is not present here, and for all of you, that we are starting our quiz from today 6 p.m. It will be live, and it will be live till Monday midnight. And what I request you all to kindly attempt, whoever has not attempted the quiz 1, I request you all to kindly convey this information to all the participants that this is the last chance to attempt this quiz 1. There won't be any more chances to attempt this quiz 1. So I request you all to kindly attentively attend this quiz 1 and then quiz 2 within the time frame. So we will also once it is live, we will also announce it in the group. So, and please spread this information to whoever has not joined this session, so that they can attempt it. Yeah, the basic point that Vikas sir is wanting to make is that don't ask quiz to be opened over and over again, right? So this will be the last time. Already it was opened for 3-4 days. Now it is being opened again for 3-4 days. So after this, we will not open quiz 1. So we are going to one step serious.
strict, you may say. But quiz 2, maybe we'll see if most of you cover quiz 2, then we don't have to repeat it. Similarly, for quiz 3, we'll complete, right? Then the course is over. So please try to be punctual. Please plan your schedules. 3 days, 30 minutes, very easy to take out the time and write the exam. Please do it, right? Thank you so much. Anybody who has the book, please share with Mr. Bhaskar Reddy, shared his email. I don't have the book, and hence this is the thing. So
Actually,
yeah,
I mean, before getting out from IIT Kharagpur, I was a Prime Minister fellow. Thanks to the government gave me money, so I bought lots of books. Otherwise, I had the same situation. So yeah.
yeah, I understand. I was also to some of the books I could not get at that time. What to do? We have to get it from somewhere and then pirate it. But yeah, once you are now able to afford, please try to buy the
Yeah.
books.
So one
Once you
good
buy the
news,
book,
sir.
you will value the book. That's what he's carrying the book. You can see.
Yeah. Yeah.
So if you buy it, then you will read it. Then you will spend some time with it. Otherwise, we'll store it, and then it's not going to really worthwhile. Yeah, anyway, that's personal choice. Please, anybody who has, please share. We will meet tomorrow at 2 o'clock. 3 hours is the lecture. 6 p.m., another 1 hour from now, the quiz will start. And
Right.
please take the exam. Mustafizur sir, thank you so much for your valuable time. Tomorrow, we'll meet at 2 o'clock. Right.
Sure,
Thank you.
sure, sir. Sure, sure.